In this section, we're going to introduce the idea of finding rates of change of functions. The rates of change have similarities to the slope of a line that would contain 2 points. Any 2 points that we pick out can define a single line that passes through those points. When we look at slope, slope is the change of y, or delta y over delta x, change of y over change of x. In measuring change for 2 ordered pairs, x1, y1, x2, y2, we find the difference then between their y's, difference, subtraction, finds difference, which really tells you the distance between 2 points. And so we're measuring the change up and down divided by the change, the horizontal change, left to right. This is the idea that we start with when we're talking about rates of change. When we take it into the notation of a function, when we talk about the average rate of change of a function, f of x, remember f of x is a stand-in for y. And so the average rate of change for our function f of x, or y, with respect to x, as x changes from a to b, is given by a similar formula here. We have the change in f of x over the change in x. And f of x, of course, is representative of y. So instead of going y2 minus y1, we can go, if we're going from a to b, we could take f of b minus f of a divided by b minus a. And of course, these are variables, so I could also go f of a minus f of b, as long as down here I had a minus b. So remember, those are just telling us to be consistent here with the input and the output value in measuring those subtractions. In subtraction, order does make a difference. So if we're going with this y, then we need to match it up with its input, b. And if this is my other y with the a input, we need to match it up and subtract the a second. So let's look at an example when it comes to a table that's given to us, where a car moves along a straight test track, and the distance traveled by the car at various times is shown in the table. So we have different times and different distances that have been traveled at those points. So we want to find the average speed of the car over the interval from 0 to 10 seconds. So if I want to find the average rate of change, again, this can be thought of as a slope. I'm going to take the f of 10 minus the f of 0 and divide that by 10 minus 0. So the f of 10 represents 10 as the input, and the f of 10 would be the output, the result. In this case, the distance traveled. At 10, we see that distance traveled is 140. So this would be 140 minus the f of 0. Well, the distance traveled at time 0 is 0. So we have a 0 there. And on the bottom, we're going to go 10 minus 0. So because of those zeros, we see this is simply 140 divided by a 10, which is 14. This would be 14 feet per 1 second, or 14 feet per second. For the second one, let's go from 15 to 30. I do want to emphasize, I want to go back here for a second, actually, and show you that had I gone f of 0 minus f of 10, and then we have 0 minus 10 on the bottom, I would get negative 0 minus 140 over 0 minus 10, which is negative 140 over negative 10, which is also 14 feet per second. Negative divided by a negative is positive. So regardless of what order I went in there, as long as I stayed consistent matching up the input of 0 with 0 first in the subtraction on the bottom, and so on and so forth there, we end up with the same answer. It doesn't matter. So I'm going to just keep it with the definition here in terms of the order. So I'm going to put f of 30 minus f of 15. So the distance at 30 seconds compared to or minus the difference at 15 seconds. And then this will be 30 minus 15 on the bottom. So on the top, at 30 seconds, we're at 1,800 feet. And at 15 seconds, we're at 400 feet. And then we have 30 minus 15, which is 15. So this gives me 1,400 divided by 15. We get 93.3 repeating feet per second. We can see here that this, what we did here was definitely not a linear situation, because had this been a consistent acceleration, which would produce a straight line, so a consistent speed, it doesn't matter what 2 points we would pick, the speed would be the same. The difference of the y's over the difference of the x's would be similar. And we can see this even more when we look at it from a graphical standpoint. This one, we're looking at the number of women with PhDs between 1960 and 2000. And of course, this is given in, X is given as years since 1990, or 1900, sorry. So here's my first input here. And we're going to do it from, this is kind of created, if you'll notice here, from some specific points, but the graph is an approximation of those. So we're going to use the approximate values on the graph. Let's put this in a more of a bright tone there. And then the year 2000 would be up here. And we're going to have to estimate that one because it isn't necessarily given to us. But it's about a little less than 1,800, so I'm going to say 1,750, because 17,000 would be the in-between there. And this is number of women earning PhDs. So I'm going to write my 2 points there. We're going to put 100, and we're going to put its approximate value, 17,500. It's a little bit more than half. So that in between would be 17,000. I think it's a little more, maybe half of that, in the upper half of that. And then on the bottom, we're going to put the 1960, so 60 and 2000. So what we're finding really is the slope of the line that would connect these points. So we're treating this as 2 points on a graph that's not a straight line, but we're basically finding the slope of the line that connects those points. So we're going to take our f of 100 and subtract the f of 60. Then we're going to go on the bottom, 100 minus 60. So that gives me my 17,500 approximation there, minus 2,000. Divided by 100 minus 60, which is 40. Doing the division there gives us an approximation of 437.5. And then we want to think of what are the y and x values here. This is 437.5 over 1, right? Any whole number that we have, or number with a decimal too, we can think of as just being over 1. And so this is we look at the y's. Remember, the y is on the top. Those are PhDs, women with PhDs. And the bottom is years since 2000 or 1900. So the average rate of change here between 1960 and 2000 is 437.5 PhDs per year since 1900. And that's between the years of 1960 to 2000. When we're just given the function itself, we just have to do some plugging in to find these. But again, the average rate of change, the slope, is going to be, here we're going from here to here. So I'm going to find the f of 4 minus the f of negative 1 and divide that by 4 minus negative 1. So we do need to figure out what is the f of 4 and what is the f of negative 1. So let's just go with the 4 first. So this would be 4 cubed minus 3 times 4 squared minus 8 times 4 and then plus 6. Well, 4 cubed is 64, so that's 64 minus 4 squared is 16, and 16 times 3 is 48. So this is minus 48, and then minus 32, and then plus 6. So doing this summation, we get negative 10. So that is my f of 4. I'm going to go ahead and just put that up here, minus 10. And then we need to find the f of negative 1. So that is negative 1 cubed minus 3 times negative 1 squared minus 8 times negative 1 and then plus 6. Well, negative 1 cubed is still negative 1. Negative 1 times itself 3 times. Still ends up with a negative number. And then we are going to subtract 3 times negative 1 squared. Well, negative 1 squared, we do that first. It becomes positive 1. So this just remains minus 3. So negative 1 minus 3. And then this is negative 8, negative 1. That becomes plus 8 and then plus 6. So negative 1 minus 3 is negative 4. Negative 4 plus 8 is 4. And then we add 6, so we also get 10. And so we write in 10 up here. And then 4 minus negative 1 is 5. And so this gives me negative 10. Negative 10 minus 10 is negative 20, because we could make this plus negative 10. See it a little clearer there. And then we divide that by 5. Negative 20 divided by 5 is negative 4. So the slope of the line from negative 1 when we go to 4 has a slope of negative 4. And this is how we can find the average rate of change for functions.